Hi everyone. Addressing your feedback from today's lesson, um, I have one question here. Does the rate determining step always have to be the first step? No, actually, it will frequently not be the first step. And so yeah, short answer to that is no, it won't always be. And we actually saw an example of that today when we were doing the blue bottle experiment, where the first step, which is driving oxygen into aqueous through shaking, that happened relatively quickly, and that was the first step in the reaction mechanism. That was one of the faster steps. And then the rate determining step, the slow step, was actually converting the methylene blue dye from its oxidized form back into its, which was blue, back into its reduced form, which was clear. And that was like the last step in the reaction, and that was the rate determining step because it took so long for it to occur. So no, it won't. It won't always be the first step. Is the slow one. And then I got another request. Can you go over the reaction orders again quickly, discussing how keywords can tell you which order it is, i.e. looking at graphs, the dependence of concentration on time, so on and so forth. Yeah, sure. This is not meant to be any type of replacement lesson. This is just meant to be sort of like a very, very quick crash course summary about how to interpret graphs of reactions and reaction orders. So up here I've very quickly or messily recreated that table I presented in the PowerPoint. I had another request question, can you please post the PowerPoint? Yes, absolutely, I will. But basically what this table is summarizing is for each of the different orders, what is the relationship between the rates and concentration. That's what's given in the rate laws. And I also have the integrated rate laws, which relate concentration and time. So rate laws on their own are good for showing, again, the relationship plots of rate versus concentration. Integrated rate laws, on the other hand, give you a relationship between concentration and time. So in the context of today's question, I'm actually going to start with the integrated rate laws, because that's what that question was about, and how to interpret these plots. Basically, the idea is that in practice, you can't predict the order of a reaction. You need to determine it experimentally. So one thing that you can do is you perform the reaction and you measure the concentration as a function of time. As the reaction proceeds, you keep measuring the concentration over time. Once you get that data, you plot it up. And you plotted it in a few different ways. You plot the concentration versus time, you plot the log, the natural log of the concentration versus time, and you plot the inverse of the concentration versus time. So normally you take all your data, because again, you've measured concentration and time, so you need to recalculate some things for your data, convert it into natural logs, convert them either into reciprocals, and then plot up those terms. And so the idea is that when you make those plots, if it's a zeroth order reaction and you plot concentration versus time, then you get a linear slope or a linear line. Why is that the case? That is the case because zeroth order reactions do have a linear relationship between their concentration and time. That's not true for first and second order reactions. So if it's not a zeroth order reaction and you try plotting the concentration versus time, you won't get a linear line. You'll get something that sort of curves upward maybe, or maybe it curves downward, or it does some other unusual thing. And if you plot out the concentration versus time, you see something like this, then you know it's not a zeroth order reaction. So that's how you utilize integrated rate laws, is you plot them up and you plot out your data versus time in a few different ways and see which one of those ways gives you a linear curve or a linear plot. And depending on which one of those is, that's how you identify the reaction order. And similarly, so for like a first order reaction, if it's a first order reaction and you plot the natural log of the concentration versus time for your data and you get a straight line, then you know it's a first order reaction. So I tell you what, I'll try doing these curves a little bit differently. So maybe I'll say that the blue curve is going to be for a 0th order reaction. The red curve would be for a first order reaction, and then the green curve here would be for a 2nd order reaction. So one set of data, these are each going to refer to different reactions, so I'll call the blue one reaction 1. I'll call the red curve here reaction 2, and then the green curve will be reaction 3. And again, I'm not saying that these are different reactions, the same reaction that I'm running in different ways. They are completely different reactions. Like A plus B goes to C, D plus F goes to G, like completely unrelated reactions that have different rates and different rate laws. So let's say I plot out all of the concentrations versus time, and hold on one second, I'm going to pause this video. Hi everyone, just continuing my discussion here. So let's say you plot out your concentration versus time, only one of them gives you a linear curve, so that implies that the reaction 1 here is 0th order. If I plot out the same reaction data as the log of concentration versus time, then I predict I'm going to get something that looks maybe like that. So it kind of curves, maybe make that a little bit more clear. Maybe that one curves down a little bit like that. Versus reaction 2, maybe its curve looks like that. And then reaction 3 here, different reaction has a curve that looks, maybe I'll make that again, make that a little bit more obvious. That one looks something like that. So it definitely has some curvature to it. So based on these observations, what I would say is, okay, only reaction 2 gives me a straight line when I plot the log of the concentration versus time. And the only reaction order that gives you a straight line when you plot its natural log versus time is if it's a first order reaction. So that implies that reaction 2 here is first order. And let's say I try plotting their concentrations as 1 over the reciprocal versus time. So what I predict that I get here is something that looks like that for the first order, or rather for reaction 1. Reaction 2 might look something like that, which is also not straight. And then reaction 3 here has a nice straight linear curve, which implies that reaction 3 here is, oh goodness, second order. So in terms of utilizing rate laws, that is one way we frequently try to use them. We take a set of kinetic data where you perform a reaction, measure concentration and time, and you try plotting it in different ways and see which one of those plots gives you a linear curve. And based upon that, that lets you figure out what the reaction order is. So, yeah, basically if you see a linear curve for concentration versus time, it's going to be 0th order. If you see a linear curve for a log versus time, it's a first order reaction. And if you see a linear curve for inverse concentration versus time, it's a second order reaction. So other questions here are, what are these plots going to look like if I plot rates versus concentrations? So those are going to look like this. So I'm going to be plotting up here again, rate versus concentration. And for that, you can again kind of look at just what do these equations, what would those plots look like? So for a 0th order reaction, the rate is actually independent of the concentration. Or if you want to think about it this way, it goes as concentration to the 0th power, meaning 1. So if I were to plot that out, the rate should be flat. The rate constant here, the actual value of this should just be equal to the rate constant for that reaction. So this would be if you have a 0th order reaction, again, because the rate is completely independent of concentration. Let's see here. For a 1st order reaction, so I think I was using red for a 1st order reaction, the rate goes as the 1st power of concentration. So if you want to think about rate as being your y variable, k is like your slope, and then concentration is my independent variable. X is your x variable. So I predict this is going to have a slope of k and a y-intercept of 0 because there is no added term on there. You are adding a term, it's just adding 0. So that curve should look like this for a 1st order reaction. And if I'm looking at my 2nd order reaction equation here, and I look at the rate versus concentration, it's going as, well, rate would be my y variable, the slope here, not really the slope, but the prefactor here would be my k, and then x is now going as the square of, it's now going as its square. So if I were to plot out that, I would expect to see a parabolic, or is that, yeah, half of a parabola. It would look like y equals x squared. So these are the different plots I would expect to get for 0th, 1st, and 2nd order reactions. Again, that's if I plot rate versus concentration. So the last type of plot you might be able to produce is a plot of not rate versus concentration, not concentration versus time, but rather rate versus time. And even though there's no equations for that, we can sort of hypothesize what they should roughly look like if I were to make plots of them. So if I put here rate versus time, so let's see here. For a 0th order reaction, the rate depends on the concentration for the 0th order reaction. But I take that back. No, it doesn't, because it's going as concentration of the concentration of it's going as concentration to the 0th power, so it should actually just be flat. So what we expect here is to yet again have a flat curve for the 0th order reaction. Even though concentration changes with time, concentration decreases, the rate doesn't depend on the concentration for a 0th order reaction. So that should be constant with time. For a 1st order reaction, the rate depends on the concentration, but if you rewrite the integrated rate law for concentration, if you undo these natural logs, you can write an expression for the concentration at different times and its dependence on time. So if I make this substitution in here, then what I expect for my rate is that the rate should decay exponentially. Let me get a different color here yet again. So again, that would be for a 1st order reaction. So you can sort of, again, rationalize that to yourself, that the rate depends on the concentration. The concentration decreases exponentially with time. So as a result, the rate decreases exponentially with time. So that's That's a substitution we could do there. This one, you can also make a similar substitution. So I rewrote this. I moved over my denominator to over here and moved all of these species underneath the quotient line. So what I get here is an expression for concentration versus time, and I'll just put the proportionality here, roughly speaking. The proportionality is that the concentration depends on 1 over time. Or conversely, that 1 over the concentration is proportional to time. These two equations are equivalent to each other. The relationships are equivalent. So I can substitute this expression. Get rid of that. Substitute that expression up here, and then what that predicts is that rate should depend on k times the square, 1 over the square of time. So it should be proportional to that. So it should have an inverse relationship, but a fairly sharp inverse relationship, which is not going to be quite as sharp as an exponential decay. So that one should look basically like that. Did I get that right? No, I take that back. It's actually going to decrease more quickly. That's right. It will decrease more quickly. So it will actually look like that, more or less. So I'll do that over here. This is for a second order reaction. So yeah, that is a very, very quick summary of just generally how do the plots relate for rate versus concentration, concentration versus time, and rate versus time. So yeah, so that's that. So if you have any additional questions about the relationship between reaction rates, time, and reactant concentrations, and how to interpret those graphs, please, I would be very happy. I'm always here for office hours, and I'm here, throughout the day for open door policy. So just stop on by, and I'll be happy to address any questions or concerns you have. Take care, folks, and I will see you all on Friday.